Okay, I'm going to continue with the homework problems from chapter 7 and 8. Okay, so this is 8. This is the one we just did. Okay, we just did that one. Okay. Okay, so this is number 17. All right. So, okay, you can put it on pause, look through the problem. Okay, so the person slides down the ramp. Okay. They start at rest. Okay. Oh, no, they don't start at rest. They start at that speed. There's my V0. Okay, so I drew the only important force I need. There's my kinetic friction force. Okay, and since I'm in the energy chapter and we've done this a lot, okay, now we know that kinetic friction is always mu sub k times n. So we've done this a lot that without even drawing the other forces, okay, you can picture in your head, okay, what the forces look like, so you know that n is mg cosine. Okay, we've done that many times. Okay, we broke up the mg sine, right? Mg cosine, mg sine, and so on. Okay, so that's why I wrote that one there. Okay, they gave me the mu sub k, and they'll know how much energy is transferred to thermal energy. Okay, so again, that's why they're not saying what's the work done by friction, because we don't know the work done by friction. Okay, but we can talk about the kinetic energy dissipated by the kinetic friction force. Okay, or the energy lost or converted to heat. Okay, so in our energy expression, that's that term. Energy lost to friction is F sub kd. Okay, and F sub k is mu sub k n. Okay, F sub k is mu sub k n, and n is mg cosine. So here I have mu sub k n, but don't forget the d. Right, there's the d right there. Okay, so I put that in, and that gives me my energy lost or dissipated by the kinetic friction force that gets converted into heat. Person gets warm, ramp gets warm. Okay, now they want the speed at the bottom. Okay, all right, so let's see. So here's our go-to energy expression. Okay, that we know. That's kind of like the lab that we're doing now. We rolled a ball in the tube from ball started at rest in the tube, got to rest there, and we were actually able to calculate the difference in that potential energy. Okay, the energy dissipated by friction that was converted into heat in the tube. So this term, energy lost, we know. Okay, 71.2 joules of energy are lost along the ramp. Okay, this term, work done by non-conservative forces. Okay, so remember, you have the normal force, okay, but it's perpendicular to the displacement. So normal force does no work. So there are no non-conservative forces that do work. So that's 0. Okay, so remember, delta E is final minus initial. So I brought the E initial over, make it look like that. Okay, here's my reference point. Okay, so initial energy is kinetic and potential. Final energy, kinetic and potential. Okay, and I'm trying to find V final. So I'll go through each of these terms here. So there's my K final. Final potential energy at the ground is 0. Initial kinetic energy, they gave me V0, and the energy lost is that. And then I can get my final speed as a number. Okay, so this looks really complicated, but I think I did one of these in our notes to show that you don't have to do this in steps. Okay, that's the whole beauty of conservation energy. If you can write down the initial state, write down the final state, you can take into account any energy gains and losses due to work done by non-conservative forces and any energy losses due to kinetic friction. So here's my initial energy state, point A. Here's my final energy state at B. So I'm going to go from A to B. And here's our go-to expression, okay? And they want to find, okay, so I know how fast it's moving here. And they want to find, if the block stops there, they want to know, where is it? They want to know how far does it slide. They want to know this distance D. Okay, so I had to pick a reference point for potential energy. Since I have no idea what that height is, okay, I have no idea what that height is. Whoops, I don't know what that height is. So that's why I chose my reference point up here, because I know all the heights with respect to that height. Okay, so that term 0, okay, and remember E loss is F sub kd, all right. Oh, and remember, this is 0 because I just drew some normal forces here. There's a normal force at that point, normal force at that point, okay, And remember, normal means perpendicular. In all those places, the normal force is perpendicular to the direction it's headed. Okay, work done by normal force would be 0 because of the 90 degrees. Cosine of 90 is 0. Okay, so I wrote E final minus E initial is E lost. Okay, remember E lost is F sub K D. Okay, now remember the energy is lost up here on the flat area. Okay, and on the flat area, normal force is mg. So kinetic friction force is mu sub K mg. So that's what I wrote right here, mu sub K mg. And then don't forget the D. Okay, because mu sub K mg is a force. Okay, the D is there because it's an energy, right? Force times the distance is an energy, or like work. Okay, so my final kinetic energy is 0. It's at rest at B. Final potential, mgh. Initial kinetic energy at A. Initial potential at A is 0. And then I have everything in here to get D as a number. Okay. Okay, so take a look at this one, and you can hit pause, read through this. All right. So essentially, this thing's moving. Okay, and I called it V0. And it says, okay, they want you to find... What did I call it over here? I probably called it V final. They want you to find what's the speed of the block as it passes point B. Okay? It says if it can reach B, where the friction ends, what's the speed? And if it can't, then what's the greatest height? Meaning if it stopped over here, they want to find that height. Okay? Now, first, I'm going to assume that it does reach point B, that it's moving at point B, and we're going to find that speed. Okay. Now, how can we make that assumption? Okay. How will we know if this assumption is wrong? Well, if I assume that it's up here at point B, and I try to calculate the speed, if my final answer has that the speed is the velocity at B or the speed at B is the square root of a negative number, that means that there is so much friction it never got to that point. So we'll have to see whether or not we have a real solution at that step. Okay, so I read you the picture. Okay, and some things I needed, remember this thing is moving this way. Oops, there's my V final. Okay, so I needed kinetic friction. I didn't have to draw these forces, okay, because I kind of argued. We already know N is mg cosine, okay. But here's our go-to energy expression. Woo, like that, okay. Where energy lost is that term, F sub Kd. While it's sliding, normal force does no work, so that's 0. Okay, and again, I'm going from A to B. Okay, so this becomes that expression. Pick my potential energy reference point to be there. So I wrote my final energies, my initial energies, okay, and I put in for each one. So there's my K final. Okay, now my final potential. Okay, final potential energy is mg times the height. Okay, times that height. Okay, times that height. So my U final is mg times that height. Well, what is that height? I didn't draw it down there. Okay, so that height is this h, which they give us, plus this part, whoops. Nope, okay, plus this part right here. Okay, so they give us theta. Okay, so they give us theta. I know theta there. So essentially I have a triangle. It looks like this. Okay, I have theta. I have that distance L. And I'm trying to find, what did I call it? I didn't call it anything. I'll call it distance D. Okay, so this distance D is L sine theta. So the total height at B, okay, is h, there's my h, plus L sine. So that leg is L sine. So that's my total height above my reference point for potential energy at B. Initial kinetic energy, 1 FmV squared, initial potential 0. Here's my energy loss term. Okay, don't forget the D. Okay, leave off the D, it's not an energy term. Okay, then I have everything in there except for V final. And so indeed, that was a positive number. Okay, which means that it did get to point B. Okay, so here's number 21. Okay, take a peek at this one. You can put on pause. All right, so basically, someone's going to let go of that. Both of these are going to move the same distance. Okay, if this one falls 25 centimeters. This one also moves up 25 centimeters. Okay, and they want to know release from rest. Okay, what's their total kinetic energy? So I'm solving for K total. Okay, now I drew two, or I picked two reference points. So the lowest point that M2 gets is here. So that's potential energy reference point equals 0 for number 2. Here's my lowest point for number 1. There's my potential energy reference point for number 1. Okay, here's our go-to energy expression. Okay, normal force does no work. All right, now, oh, and there's no kinetic friction. All right, now, are there any let's look at what non-conservative forces act on the system. Okay, normal force does no work, but you have the tension, and tension. Okay, so the tension is a non-conservative force. Okay, but if I choose this dotted line as my system is both masses, then the tension right there, that tension force is internal to my system. Okay, so it's not an external force that does work. So there are no external non-conservative forces that do work. So this whole term is 0. So energy is conserved. So let's see. So I wrote down my final for number 1, final for 2, initial for 1 and 2. Okay, and then went through each term. So initials are easy. Initial kinetic is 0. Initial kinetic is 0 for number 2 because they're not moving. Initial potential for number 1, I chose that to be 0. Okay. Initial potential for number 2, I chose that to be 0. Okay. I'm sorry, not the initial potential. Whoops, where'd it go? No, that's not 0. That's okay. Okay, so these are okay. Those are 0. Okay, and then what I have left is I'm trying to find the final kinetic energy. So what I did is I called K1 final plus K2 final. Instead of writing two terms, I called it K final 1, 2. So this is the final kinetic energy of 1 plus the final kinetic energy of 2. Okay, so the only terms I had left, I had that one left, okay, which I threw over here because my K1 plus K2 is on the left, so I threw this one over here to make a negative, and then this one is still sitting over here, it's positive. Okay, so initial potential energy of number 2, okay, is M2G times the height d. Initial, and then the final potential energy of number 1. Number 1 is now up here. Okay, so it's gone up by a little height. So this little triangle here, okay, I drew it right there. Okay, so this triangle right there I drew here. So it slides up the inclined distance d. There's the angle theta right there. There's my height h. Okay, so I needed to find that height, and h is d sine theta. I have right there. So this height here is my d sine theta. Okay, and I know that as a number. All right, and then what I did is I factored out a g. I didn't have to, but I factored out a g. Okay, and I calculated my final kinetic energy. All right, now so that's done. Okay, now I said that the work done by the non-conservative forces was the work done by the tension 1 and tension 2, meaning this is the tension acting on number 1, that's the tension acts on number 2. Okay, so if I look at my picture, tension 1 points upward. Okay, here's tension number 1 pointing upward. The work done by tension 1 is tension 1 dotted into the direction it's going. So it's tension 1, okay, times the distance to which it moves times the cosine of 0 degrees, because it's moving in the same direction as the tension. Cosine of 0 is 1. So that's the work done by tension 1. Okay. Work done by tension 2 points up. That's tension 2 right there. Okay. So work done by tension 2 is tension 2 dotted into the displacement. So it's the tension times the distance it's moving times the cosine of the angle between them. One points up, one points down. Cosine of 180 is -1. Okay, so, and remember, these tensions are equal. Okay, the tension in the string is equal. So T1 is equal to T2. Right? T1 is equal to T2 is equal to T. So where to go? So work done by T1 is TD, work done by T2 is minus TD, so the net work done by the non-conservative tension force, okay, the net work done is TD minus TD is 0, okay? So if you take it as a system, okay, the net work done by tension is 0. Okay, one work is positive, one is negative, because the tensions are internal to the system. They do no net work, okay? But if you just look at one of the masses, okay, if I just look at one of the masses, okay, look at number 1, okay, number 1 sitting there, now you let go, now it starts to move. Why did number 1 start to move? Okay, that's because tension came by and did work, okay? So if you look at them individually, okay, then tension number 1 does work on M1 to speed it up, okay? Tension number 2 does negative work on number 2 to prevent it from being in free fall, okay? So energy is not conserved for mass 1, okay, because tension number 1 does work. Energy is not conserved for T2 because it's not in free fall. Tension 2 does negative work. But if you take them as a system, okay, as a system, then those tensions are internal to the system, and energy is conserved for this system. Okay, here's number 25. All right. Okay, so basically they give you a car, and they tell you there's a drag force, a resistive force, and I don't want to use F. Okay, I'm going to call this resistive force R. I called it R. This is my resistive force. Okay, so it could be right. It says it could be due to like air drag or whatever. Okay, so it points backwards. Car's headed to the right. Okay, so the car is accelerating. So there has to be a net force on the car. So that means there has to be a big blue force that has to point to the right to accelerate the car. All right. Now, they give us this function. Where's that function? They give us this function. That's the force. That's a drag force. And they tell us that as long as I put V in meters per second, that number is going to pop out in newtons. Okay. Well, why is that? Well, what would be the units of the 390? Okay. Well, it would be newtons. Okay. Well, what are the units of the 1.1? Well, I went up here and I said, okay, well, this whole thing has to have units of newtons because I have to add newtons plus newtons. So 1.1 V squared has to have units of newtons. So I said 1.1 V squared, okay, I'm not using an equal sign, I'm using an arrow, has to have units of newtons, kilogram meter per second squared. Okay. Well, V squared has units of meter, or V is meters per second. So V squared is meter squared second squared. Okay. All right. And then I just rewrote this here. I canceled out things on both sides. So I canceled 1m there with that exponent. I canceled these exponents cancel. Okay. And I'm left with an m here. And I'm left with a kilogram there. Okay. So if I bring the m on the bottom, okay, that says the only way that this stuff on the left can equal that stuff on the right is that I'd have to have this unit of kilogram meters next to the 1.1. And that's what I did. Let's see. I put it right there. Okay. So the function given, okay, really should have units. Okay. So 390 has units of newtons and 1.1 has these units. So if you stick in V in meters per second, you're going to get units of newtons. Okay. So they ask for what's the power required to accelerate the car, okay, at that acceleration when the speed is that. And I just converted the speed to meters per second, okay? So if they ask you to find the power required to accelerate the car at a certain speed, then they're asking you for the instantaneous power that that force is giving to the car, okay, to accelerate the car. So which force are they talking about? They're talking about this force, okay? That force doesn't accelerate the car, right? It hinders its acceleration. So this is the force they're talking about, okay? Calculate the power of this force, okay, required to accelerate the car. So it's instantaneous power because the speed, right? They want to know what's the power when it's at that speed, at that instant. So from our notes, to find the instantaneous power, I take the force dotted into the velocity, okay? Well, they gave me the velocity. That's my 80 or 22 meters per second. But I need what's the force, what's that blue force being exerted on the car, Okay, so I apply F equal ma to the car. I drew my forces in the x direction. Okay, I have my coordinate system. Okay, so I have the blue force points to the right. I have the resistive force points to the left. That's equal to ma. So I solve this for the force accelerating the car. Okay, not the net force, but the force accelerating the car. Right, the net force would be the blue one minus r. Okay, right. So that's my net force. Okay, but I'm looking for the force that causes the car to accelerate. So I just wrote this by itself. All right. So here's r. That's the function r. Okay, and I don't know the mass of the car. They give me the weight. Okay, so I could calculate the mass of the car, but I just multiplied top and bottom by g over g. So mg is the weight of the car. All right. So here I have my r. There's r. Okay, and then I have mg. So my mg, there's mg. A, there's a, and then my g on the bottom is that. So this is the force that's accelerating the car, all right? And so the instantaneous power, okay, is the force dotted in the velocity. And the force points to the right and the velocity points to the right, so the angle between them is 0 degrees, all right? And that gives me my instantaneous power that the force is delivering to the car at that instant in watts.